Hi again, guys. Last lesson we were looking at the black body spectrum. So this lesson I want us to look at Earth's infrared spectrum, or more specifically the infrared radiation spectrum of the atmosphere. So this is a graph which shows black body radiation curves of the atmosphere. Planet Earth is very similar to a black body, and that's why it does actually have this sort of shape here. Now, the different color lines show different temperatures of planet Earth. For example, the green line is 300 degrees K. The blue line is 280 degrees K, and the pink line is 260 degrees Kelvin. Now, what I want you to imagine is that you are, for example, 70 kilometers up in the atmosphere, and you are looking down on planet Earth. And you can see, for example, the ground 70 kilometers below you, and the ground is at 302 degrees Kelvin, this figure here. 302 degrees Kelvin is about 30 degrees centigrade. The red line here, this squiggly red line, you can see it down here as well. Yeah. The red line measures the energy leaving Earth as seen from 70 kilometers up looking down. For example, if we look at a wave number of 800 and we go up, it's about there, and then we go across, so we can see at a wave number of about 800 the energy leaving planet Earth at 70 kilometers above the ground would be about 0.41 watts per square meter. So we're going to be inputting different greenhouse gases, for example carbon dioxide, methane and ozone, and we're going to see how it affects how energy is leaving planet Earth. So we know today that the concentration of CO2 in the atmosphere is 390 parts per million. Let's enter that figure and wait for the graph to react. Okay, very interesting. We can see at this frequency here, about 700 centimeters, the rate of flow of energy leaving planet Earth has reduced. I mean, it was about 0.45 watts per square meter at this frequency, and now it seems to have reduced all the way down to 0.13 watts per square meter. And it turns out that at about nearly 700 cycles per centimeter, that is the actual bending vibration of carbon dioxide. Let's have a quick look at the bending movement of carbon dioxide. So the asymmetric stretch of carbon dioxide and the vertical bending moment of carbon dioxide both produce a dipole, which means that they are infrared active. So the molecules will react to infrared radiation leaving planet Earth. If we look at the graph at the top, we can see that the bending moment is about 600 or 700 centimeters or cycles per centimeter. So let's go back to the plot again. So here's the reduction shown, at about 600 or 700 cycles per centimeter. So we know that that is CO2. Now, if we were to measure the area between the green line and the red line, that would tell us how much heat is being trapped because of the greenhouse effect due to CO2. Now, obviously, this is just a model, and some people don't believe in models, don't think models are very accurate. So it's always good to compare the model to real life measurements. So one way to take real-life measurements is from satellites which are orbiting planet Earth. So let's have a look at a picture taken by a satellite. Okay, this is an actual picture from a satellite. It's the graph plotted actually from measurements taken from a satellite flying in an orbit around Earth. As you can see, we have exactly the same shape black body radiation curves as were shown on the model plot. Now, the units are different here, but it's the same story. So the blue area here is the energy which is being kept on planet Earth because of the greenhouse effect. Now, how much is the greenhouse effect? Well, if you look at the units on the left here, which are different to the units on the model, but you can see without the greenhouse effect it would be 180 units, but with the greenhouse effect the actual irradiance is only 40, right? So there's been a reduction in the amount of electromagnetic radiation leaving planet Earth at a frequency of 700 cycles per centimeter. Okay, let's go back to the model again. Here's the model. And let's try putting in a few other trace gases into the atmosphere and see what happens. So we have methane. Methane is also infrared active, which means that it will be heated by the infrared radiation leaving planet Earth. Now what I want you to look at is I want you to look at the graph around here when I put methane into the atmosphere. So at the moment methane levels are at 1.7, I think 1.7 parts per million. So let's enter that in. And you can see that the actual shape here has changed. The area under the green line here, between the green line and the red line, shows us how much methane is absorbing long-wave radiation from planet Earth, which isn't finding its way out into space again. And so it's also assisting the greenhouse effect. Let's go back to the satellite observation. Yes, here's the satellite observation, and we can see just here, which is exactly the same places as in the model here, we can see that the methane, which is colored yellow here, yes, is stopping radiation leaving planet Earth. Okay, next I think we should look at ozone, O3, ozone. Let's go back to the model again. So we can expect ozone to vibrate within this sort of frequency range here. Let's see what happens when we add ozone to the atmosphere. Now the amount of ozone in the troposphere is only about, I think it's 34 parts per billion. I'm just going to add in a scale of stratospheric ozone here as well, and I'll see what happens around this area here. Okay, we can also see that the ozone is restricting long-wave radiation from leaving planet Earth as well. That's what the model says. Let's just go back and see what the satellite says. And the satellite says it too. Just as a matter of interest, the frequency is about 1060, something like that. Let's have a look at the model again. Yes, the same frequency, about 1060, yes. So we know that this here is caused by carbon dioxide, this here is caused by ozone, and this here is caused by methane. Let's go back to the picture again. CO2, ozone and methane, but then water. Water vapor is a greenhouse gas, but scientists like to call it a feedback mechanism, and we'll be talking about that in the future. So once we add water to the atmosphere, we can expect to see a reduction in radiation leaving planet Earth in these sort of ranges here. Let's have a go at doing that on the plot. Now, the quantity of water vapor in the atmosphere doesn't stay the same all the way up to the atmosphere. In fact, once you get above 7, 8, 9 kilometers, there's very, very little water in the atmosphere. So we can't give a figure of what percentage of water there is in the atmosphere. We have to use a scale instead, and we're going to use a predetermined scale of 1. So let's see what happens. Okay, and immediately you can see, the red line was up where the green line was, but now we can see that there's been a terrific amount of radiation which isn't allowed to leave planet Earth. Really between 200 and 600 centimeters, and if we look over here at about 1,400, between 1,400 and 1,600, also a lot of radiation is getting trapped into the atmosphere because of water. Let's just go back and have a look at how the satellite sees it. Yes, here you can see in these regions, yes, the satellite gives the same sort of story as well. What I think is very interesting is that the model and the satellite data, or the plotted from the satellite data, are so similar. So that's the greenhouse effect for you, caused by water, carbon dioxide, ozone, and methane. One must remember that the greenhouse effect is actually a very good thing. If it wasn't for the greenhouse effect, planet Earth would be much, much colder, and there probably wouldn't be humans living on it. It would just be too cold for humans. Greenhouse effect is good, but it's the change in the greenhouse effect, the global warming, that's the thing which scientists are worried about at the moment. Okay, see you next lesson.